All right, this has been a pretty long section. This is the first time I think we've ever needed 4 videos, and so this is the last video for section 5.1, and it's about story problems for quadratic functions. So let's just go through this story problem. My phone just beeped at me. All right, so Connor wants to enclose a rectangular space for a new garden within his fenced backyard. Connor has purchased 80 feet of wire fencing to enclose 3 sides, and he will use a section of his back fence as the 4th side. How can Connor maximize the garden area with the given fencing? So let's draw a picture of the scenario. This is really helpful to me in a lot of story problems. So let's say this is his backyard, and here's the existing fence. Here's the existing fence. And he wants to, within this, wants to fence a rectangular space for new garden. So he's going to have 3 sides new, right? I don't know if it's going to be longer than it is wide, but that's why I'm drawing it. Here's the 3 sides that he's going to have new. He's going to have this side, the heights here, and then the length here. Okay, so here's a picture of this scenario. Let's find a function that relates the length and width to the perimeter of the enclosed garden. Well, let's just go ahead and call this the width, I guess. And we'll call this one the length. And then this is also the width because it's rectangular. And so we know that 2 times, let's use W for width and capital L for length. And we know that twice the width plus the length is going to be the perimeter of his new garden. All right? Twice the width plus the length is going to be the perimeter. We know that has to equal 80 feet because that's how much fencing we have, right? 80 feet of fencing. So that's one thing that we know. Now we're going to use part A to find an area function for the enclosed garden. Well, one thing we know about rectangle area, we know the area is going to be equal to the length times the width. All right, but this isn't super useful for us because when you have 2 variables, things can change too much. Luckily, we have a restraint up here in part B. We know the length and the width are related to each other. In fact, we can rewrite this equation, 2W plus L equals 80. If we subtract 2W from each side, we get that L must be the 80 feet minus twice the width. And so what we can do with this is we can use this value in our function. So instead of writing L over here, we're going to use a function expression in terms of W. So A equals 80 minus 2W times W. And why is this better? Well, it's better because now we have A as a function of width. So we've changed it from just a formula for A to now area as a function of the width, and we've completely excluded the length. The length is dependent on the width, right? Those guys are related. They have to all add up to 80. So if we know what the width is, we can completely compute the length by doubling it and subtracting it from 80. So here is our function, area function, that is a function of the width. All right, and let's multiply it out just for fun. Make it look a little better. This is 80 times W minus 2W squared. And I'm going to read it one more time because I like to write things in standard form. Minus 2W squared plus 80W. All right, so now we need to find the dimensions that will maximize Connor's garden space and find the answer. Well, when I say maximize, when we've been talking this whole section, whenever it's been a maximum, this has always occurred at the vertex, right? This has always occurred at a vertex. And in fact, if we look at this A of W as just a regular quadratic A of W, the A value is -2, so that means that it opens down, right? Little a is -2, so I have a frowny face. So that means I'm going to have a local maximum, and that local maximum is going to be when my area is the greatest, right? So let's go ahead and find the vertex. Well, it's given by W equal to minus B over 2A, and in this case, B is 80 over 2 times -2. So that's -80 over -4, which is 20. So when the width is 20, the area will be maximized. Okay, so the width is 20. That means the length is equal to, well, let's go back and find it was 80 minus twice the width, which is 80 minus 2 times 20, which is 40. So if I have a width of 20, let's redraw my picture. Here's my back fence. Width of 20, length of 40, width of 20. Yep, that all adds up to a perimeter of 80, and my area is going to be equal to, well, there's a couple different ways we can figure it out. One, we can just take 40 times 20, which is going to be 800. Or we can use our function, a of 20 equals minus 2 times 20 squared plus 80 times 20, which is equal to minus 2. 20 squared is 400, I think. Plus, this is going to be 1600. So minus 800 plus 1600 equals 800. Either way, we got 800. All right, so that's how I did this problem. Let's go back and recap a little bit because you have a couple of these in your assignment, and they are a little bit tricky. The key is to figure out what's going on in this scenario and write one of the variables in terms of the other. Okay, one of the variables in terms of the other. This allows us to write a function in one variable instead of in two variables, which are very hard to work with. Now we have a function here in one variable. Our area is dependent on our width only. We can maximize that function because we know how to find the vertex. The vertex is going to be the maximum. The vertex is going to be the minimum. It occurs at the W value, and the output is the function evaluated at that point. So my vertex actually was 2800, right? Don't be afraid to use a graphing calculator or Desmos to help you graph these. Those can be really useful.